Okay, so we want to calculate the mass of NaOH, the mass of NaOH that would have to be added to 10 milliliters of 2.0 molar HNO3 to obtain a pH of 1. Okay, so we want our pH to equal 1, which means we want our hydrogen ion concentration to equal 10 to the negative pH, which is 10 to the negative 1, which is zero point 0.1. There we go. Okay. And right now what we have is we have the concentration of hydrogen is equal to 2 molar because it is equal to the concentration of HNO3 because HNO3 of course is what kind of an acid? It is strong. Okay? So we're going to need to take it all the way from 2.0 down to 0.1. I can see a couple ways of doing this actually. So my change in hydrogen ion concentration is, oh, actually, nah, do I want to do that? Yeah, I kind of do. So the change in hydrogen ion concentration that we want is going to be 2.00 minus 0.10, which is going to be uh, 1.90 molar. And that is the change we want. And we want it to be in 10 milliliters. Yes? So the change in moles of H plus is going to be how much of that is in 10 milliliters. So we will have 10, well, let's make that millimoles, 10 milliliters times 1.90 moles per liter. And we get 19 millimoles of H plus. That's how much we want to neutralize. That's how much H plus we want to neutralize. Right? Because we were starting with 2 molar. We want to finish at 0.1 molar. And so we need to decrease the concentration by 1.90 molar. And that's happening in 10 milliliters. So the amount of millimoles that that needs to react are 19 millimoles. So we will also need, we'll need 19 millimoles of NaOH because NaOH to H plus is a 1-to-1 ratio. Okay, and that means that the mass of NaOH is equal to 19 millimoles. Now I don't actually want it in millimoles, I want it in moles because I'm going to be using molar mass, so that's going to be 0.019 moles of NaOH times, now the molar mass of NaOH is, let's see, molar mass of NaOH, we have 23 plus 16 plus 1 is 40. 40.0 grams per mole. So 40 times 0.019 is 0.76 grams. And let's just double check our sig figs here. pH of 1.00, yeah, so we had 2 sig figs in that pH, and that meant that my concentration of hydrogen here was 2 sig figs because that was 1.00 had 2 sig figs, and then we did a subtraction. Oh, and when we did the subtraction, that gave us 3 sig figs because we went to our first uncertain digit, which is the hundredths position. So I believe we should have 3 sig figs in our answer. So 0.760. There we go. How do we feel about that? Is good? All right. Let us then take a look at number 7. Combustion of coal, which contains sulfur, produces a gaseous sulfur compound. This compound, when released into the atmosphere, undergoes a series of reactions, eventually forming acid rain. Explain this process and support your answer with appropriate equations. Now, you are expected to know that in the combustion of coal, coal is mostly carbon, but it's not the carbon that causes acid rain. Carbon dioxide will react to produce carbonic acid, but it is the sulfur impurities are responsible for acid rain, okay? Are responsible for acid rain. And why is that? Well, you have sulfur and it reacts with O2 when it burns, okay? So that's burning. And when it reacts with O2, you actually get SO2, okay? And you should recognize that that is a nonmetal oxide. And rain is made of water. So we can say that our SO2 then will react with water to produce H2SO3, which is one of the contributors to acid rain. Okay, that could probably get you most of your credit there if you wanted to be doubly sure. The next step in the reaction is you can actually have, oh, let's grab a new screen here. So we had S plus O2 gives SO2, and then we had the SO2 plus the water gave H2SO3, acid rain. Then we could actually have SO2 undergo further reaction to give us SO3. Okay, now that's not balanced, but we'll be able to balance it by putting a 2 there and 2 there, and that should take care of it. And now SO3 itself can undergo reaction with water. And that gives us H2SO. And look, now we have 1, 2, 3, and a fourth one makes H2SO4. And so you have now 2 contributors to acid rain, and this one in particular is very responsible for it because it is a strong acid. Therefore, it is a major contributor to acid rain. Yeah, yeah? And if you were writing a test on this, I would say go memorize those equations, but you're not. So, woo, okay. Okay. Let's see, where were we at? That was number 7. Number 8. Okay, a third row amphiprotic hydroxide and a third row basic hydroxide. Okay, let's go here. So we want a third row amphiprotic hydroxide, and we want a third row basic hydroxide. Now, when we talk about wanting a hydroxide, we're going to want something with OH. Okay, so you're going to need some cation. And when we talk about the third row, they're talking about the third row of the periodic table. Okay, now if we have hydroxide, OH minus, that's going to allow it to be a base. Okay, now I'm just going to pull up, I think, oh, hey, if I go to here, oh, no, I want to go to grade 9 because they have, I put in theirs a periodic table. There we go. Now, third row. Okay, so this is row number 1, has hydrogen in it. Row number 2, lithium, beryllium, etc. And then row number 3. Okay. Now, if we're going to have it with hydroxide, there's only 3 things in that row that hydroxide can combine with because hydroxide is an anion. So it needs to combine with a cation. And we only have 3 things. 1, 2, 3 that can combine with hydroxide. So let's ask ourselves, if I have sodium hydroxide, is that, we're looking for something that's amphiprotic for one of the parts of the question. We're looking for something that's basic for one of the parts of the question. So is NaOH basic, or is it amphiprotic, or is it neither? In which case we don't want to use it. NaOH, is it basic or is it amphiprotic? It is basic only. It's just going to dissociate and then, yeah, it's produced hydroxide. How about MgOH2? Is it basic? Is it amphiprotic? Magnesium hydroxide. Basic? Amphiprotic? Okay, so MgOH2, it's not particularly soluble, but when it dissolves, maybe I'll write it down here because I've got more room, so I'm going to write it down in this area here, MgOH2. When it dissolves, you will end up with Mg 2 plus 2 OH minus. Have we ended up with a solution that is acidic or basic or both? We've ended up with a solution that is basic, okay? So for the part of the question that asks who is going to be a basic third row hydroxide, that's going to be your magnesium hydroxide and your sodium hydroxide. Those ones are going to be basic. That only leaves us aluminum for our other choice, because once we get past that, now we're not looking at cations anymore, so they cannot react. Like you can't have silicon hydroxide or phosphorus hydroxide because phosphorus wants to gain electrons and it just doesn't work. So If we have aluminum hydroxide, when it dissolves, we'll end up with aluminum 3 plus, and we'll end up with hydroxides, 3 of them. How is it possible that that thing is amphiprotic? Because obviously it's producing hydroxide, so yeah, base. It's more than just Al. Yeah, there is something that happens with Al. What is it that happens with Al? Aluminum. Yeah, we feel creepy, okay? The aluminum can grab 6 waters, right? And by grabbing 6 waters, it can then lose one of those protons from water, and then we'll end up with only 5 waters. This is, of course, on your data booklet. And then there will be an H plus floating around. Okay? Yeah, so we're going to get hydrolysis is what's going to happen. I left out the hydrolysis because I kind of ran out of room on this periodic table, but yeah. Okay, so that's why that one is amphiprotic. Okay, let's go back to Chem 12. There we go. All right, and we were looking for, oh, there. Is that the right one? That's okay. Okay. Why did it move? I don't know. There we go. Okay. So we wanted 7, 8, and 11. Okay. 11, you are going to write a balanced equation showing the formation of an aqueous basic aqueous solution using the metal oxide SRO. So we want to take SRO and we want to show how that reacts to make a basic aqueous solution. Okay, well, we have here what kind of a compound is this? It's an oxide. What kind of an oxide is it? Well, it's strontium oxide. Yes, it is. More generally, more generally, what kind of an oxide is it? We have 2 basic classes or 2 major classes of oxides. It is a metal oxide. And we know that metal oxides are OH, basic, yes. So we need somehow or other for this strontium hydroxide to make, or sorry, strontium oxide to make a basic solution, which means we're going to need OH as one of our products. Where is that hydrogen going to come from? Because we want as one of our products to have hydroxide. Yeah, it's going to come from water. Okay. And strontium is 2 plus. Hydroxide is -1. So actually, if we just do SrOH2, let's see if that actually worked in terms of balancing. Oh my God, it did. How cool is that? We have 1 strontium, 1 strontium. We have 2 oxygens, 2 oxygens, 2 hydrogens, and 2 hydrogens. And that's how it produces a basic solution. And that's it. Yeah, I could give you a quiz. It would be on, let's see, what haven't we quizzed you on yet? We could have quiz on titration, calculation, um, what else? Titration curves, acid rain, and metal and nonmetal oxides.